So, assuming you could build an impossibly stable, temperature-controlled and vacuum-sealed tunnel directly through the Earth, as well as an incredibly advanced dive suit to supply you with oxygen, you could in theory survive a fall into said hole.
That the tunnel is now a vacuum also provides considerable benefits to the ease and comfort of your trip. Travelling through air always incurs air resistance, which not only imparts turbulence, but also significantly slows you down. When the force of air resistance on a falling object increases to equal that of the force of gravity, said object has reached its terminal velocity, and cannot fall any faster. Given that the average human in a stable belly down position has a terminal velocity in freefall of about 200 km per hour, or about 120 miles per hour, it's probably going to take you well over a day of falling to reach the centre. If we're now falling in a sealed vacuum, it will negate all the previously mentioned deadly issues with super hot and super dense air. And it also means a sluggish descent is no longer a problem. In the absence of air resistance, you'd be able to speed past your usual terminal velocity in a matter of seconds, and continue picking up speed at an alarming, yet probably thrilling rate. As you plummet towards the core, the resultant force being exerted on you will be decreasing. This in turn slows the rate of your acceleration as you approach your maximum velocity at the center of our planet. So, what sort of exhilarating speeds can you expect to hit at the equilibrium of your journey? Well, for your futuristic dive suit, let's use your average NASA spacesuit, as they come with a life support backpack and generally do pretty well in the vacuum of space.
Yes, I'm aware it is not a true vacuum.
One of these, plus the mass of an average human, is around 190 kilograms, or over 400 pounds. Using our calculations, this means you would hit the center of the Earth at a whopping 28,000 kilometers an hour. That's over 17,000 miles per hour, and means this half of the journey would take a little over 21 minutes. Fun fact alert, at the center of the planet, you'd also experience weightlessness, akin to floating in outer space. Unlike standing on the Earth's surface, with its mass entirely beneath you, pulling you downwards, at the Earth's center, the planet's mass is all around you, pulling you in all directions. As the Earth is near enough spherical, these gravitational forces cancel each other out, allowing you to merrily levitate like a scientist on the International Space Station. Not that you'd really be there long enough to notice, given that in this situation when you pass the Earth's centre, you'd be travelling at roughly 22 times the speed of sound. As soon as you shoot through the planet's centre, all the gravitational forces that were acting upon you before will now begin acting upon you in the opposite direction. The further and further you move away from the planet's centre point, the amount of the Earth that is behind you increases, progressively pulling against you. This will slow you down considerably as you hurtle back towards the planet's surface. This motion your body is